Could we weaponize quantum entanglement? It's a great question. It sounds like something straight out of science fiction. You picture a scientist in a lab, flipping a switch. Instantly, 1,000 miles away, a target explodes. Or a commander whispering an order, and a fleet of drones on Mars instantly receives it and attacks. That's the image we get from movies. Instantaneous action across any distance. Spooky, as Einstein called it. The short answer, the one that physicists will give you right away, is no. You cannot use quantum entanglement to build a death ray. You can't use it to send messages faster than light. You can't make a quantum voodoo doll where you poke a particle here and its entangled twin hurts something over there. It just doesn't work that way, and it's a hard, fundamental limit. It's not a matter of building a better machine. It's baked into the rules of the universe, but that's not the end of the story. Not even close. The real answer is more complicated, and in some ways, more worrying. While you can't build a classic sci-fi weapon with entanglement, its properties are at the heart of a new technological arms race. The weapons it creates aren't explosive. They're silent. They target information, detection, and communication. And in the modern world, that might be even more powerful. To get why, we have to talk about what entanglement actually is. Let's try to keep it simple. Imagine you have a pair of gloves, a left one and a right one. You put them into two separate, identical boxes. You don't know which is in which. You mail one box to your friend in Australia, and you keep the other one here. The moment you open your box and see a left-handed glove, with absolute certainty, that your friend has the right-handed glove. Instantly. It doesn't matter that it took weeks for the box to get there. The information about your friend's glove seems to arrive in your brain the second you look at yours. That's the basic idea. A connection between two things. But quantum entanglement is weirder. In the quantum world, particles like electrons have a property called spin. You can think of it like a tiny spinning top. Or it can be spin up or spin down. Now you can create a pair of particles in a special way so that their spins are linked. They are entangled. For example, you can set them up so that if one is spin up, the other is guaranteed to be spin down. And if one is spin down, the other is guaranteed to be spin up. They are always opposite. Here's the strange part. Until you measure one, neither particle has a definite spin. It's not like the gloves, where one was always the left glove, you just didn't know it yet. The quantum particles are in a fuzzy, undecided state of both possibilities at once. It's called superposition. It's like a coin spinning in the air before it lands. It's neither heads nor tails. It's both. When you measure one of the entangled particles, say the one in your lab, its state instantly collapses. The spinning coin lands, it randomly becomes either spin up or spin down. Let's say you measure it and it's spin up. At that exact same moment, its entangled twin, even if it's on the other side of the galaxy, will instantly become spin down. Its own spinning coin lands, and it lands on the opposite face. This is the spooky action at a distance that bothered Einstein. The correlation is instant. It seems to defy the cosmic speed limit, the speed of light. So, why can't we use this for a weapon? If something happens here and it causes an instant effect over there, that sounds like a perfect tool for communication or attack. This is the core of the whole misunderstanding. The key word is random. When you measure your particle, you don't get to choose the outcome. You can't decide to make it spin up to send a 1 or spin down to send a 0. You just measure it, and nature rolls the dice. Half the time you'll get spin up, half the time you'll get spin down. It's completely random. Your friend in Australia also measures their particle. They also get a random result. Half the time spin up, half the time spin down. Now, your results are perfectly correlated with theirs. When you get up, they get down. When you get down, they get up. But you don't know this until you compare notes. You have to call them on the phone, or send an email, or flash a laser beam at them. And that call, that email, that laser can only travel at the speed of light. Without that classical communication, all you have is a random string of data. And all your friend has is a random string of data. You have no way of encoding a message in that randomness. You can't force an outcome. You can't transmit information. And if you can't transmit information, you can't send a command. And if you can't send a command, you can't tell a bomb to explode or a drone to fire. The same goes for energy. Measuring the particle here doesn't send a beam of energy to the other particle. It just resolves an uncertain shared state. There's no energy transfer, so no death ray. The laws of physics, specifically the no communication theorem, put up a very firm roadblock. This entanglement allows for correlation, not causation, at a distance. You can't use your particle to do something to the other one. You just learn something about it. So the direct, brute force weaponization is a bust. It's a dead end, but let's talk about the indirect ways. This is where it gets real. The most significant threat, and the one that governments are pouring billions of dollars into, is quantum computing. A classical computer, like the one you're using now, works with bits. A bit is a simple switch. It can be a 0 or a 1, on or off. All the complexity of modern software is built on billions of these simple, definite switches. A quantum computer works with qubits. A qubit, because of that superposition principle, can be a 0, a 1, or both at the same time. It's the spinning coin, and this is where entanglement comes in. You can entangle qubits with each other. When you do this, they stop being independent. They become a single, complex system. 2 entangled qubits can hold 4 states at once, 3 qubits can hold 8, 300 entangled qubits can hold more states than there are atoms in the known universe. This allows a quantum computer to perform calculations in a fundamentally different way. It can explore a huge number of possibilities simultaneously. For most tasks, this isn't that helpful. Your laptop is better at sending email, but for a few specific types of problems, a quantum computer would be almost magical. One of those problems is factoring large numbers. This sounds boring, but it's the foundation of almost all modern security. When you buy something online, send a secure email, or access your bank account, your connection is protected by something called RSA encryption. The security of RSA relies on a simple fact: it's very easy to multiply 2 large prime numbers together, but it's incredibly difficult to take that resulting big number and figure out what the 2 original prime numbers were. A normal computer would have to guess and check, one by one. For the numbers used in encryption, this would take a classical supercomputer billions of years. It's practically impossible. A large-scale quantum computer using an algorithm called Shor's algorithm could do it in minutes. This is the first real quantum weapon. It doesn't blow things up, it lays everything bare. A nation that builds a powerful, fault-tolerant quantum computer first could, in theory, break the encryption of every other nation. They could read secret military communications, they could access sensitive government files, they could drain bank accounts and crash financial markets, they could steal industrial secrets. It would be a strategic advantage unlike any other in history. It's a crypto-apocalypse scenario. This isn't science fiction. Intelligence agencies around the world are already operating on the assumption that this is coming. They're running a race. One race is to build a quantum computer to break everyone else's codes. The other race is to develop new quantum-resistant encryption that even a quantum computer can't crack. The weaponization of entanglement here is as an engine of computation, creating a master key to unlock the world's secrets. So that's one, the codebreaker. What's next? The all-seeing eye. This is the world of quantum sensing. Entangled particles are incredibly fragile. Their special quantum state is easily disturbed by the outside world. A tiny change in a magnetic field, a slight gravitational pull, a single photon bouncing off it, any of it can break the entanglement or alter the state. Normally, this is a huge problem for building quantum computers. It's called decoherence. Scientists spend all their time trying to shield their qubits from the outside world. But in quantum sensing, you take that weakness and you turn it into a strength. You use that extreme sensitivity to detect things that were previously undetectable. Think about a stealth submarine. It's designed to be quiet and invisible, but it's still a huge chunk of metal moving through the Earth's magnetic field. It creates a tiny, tiny disturbance. It also has mass, so it creates a minuscule gravitational ripple. A conventional sensor can't pick that up from a distance, but a sensor based on a network of entangled particles could. By measuring how the environment disturbs their delicate quantum state, you could map these tiny fields and see the submarine. The same goes for a stealth bomber. It's designed to be invisible to radar. It doesn't reflect radio waves well, but it still has mass. It still disturbs the air and the gravitational field around it. A quantum gravimeter could potentially detect that disturbance. You wouldn't need to bounce a signal off it. You would just sense its presence, like a spider senses a vibration on its web. There's even a concept called quantum radar. The idea is you generate a pair of entangled photons, you keep one, and you send the other one out into the sky. If the outgoing photon hits something, like a stealth plane, and bounces back, its properties will have changed. Even if it gets lost in all the background noise of other photons, you can check it against the twin you kept, because they are entangled. The correlation between them allows you to pick your signal out of the noise. It could make stealth technology obsolete. This extends to navigation. Submarines and missiles rely on GPS, but GPS signals can be jammed or spoofed. A military that relies on it is vulnerable. Quantum sensors, specifically accelerometers and gyroscopes, could be so precise that they could track motion perfectly without any external signal. A submarine could run silent for months and know its position down to the centimeter. A missile could fly to its target without ever needing to check in with the satellite, making it unjammable. This form of weaponization is about intelligence and control. It's about removing the fog of war. It's about seeing what your enemy is doing and ensuring your own weapons can't be stopped. Entanglement isn't the bullet here. It's the perfect scope on the rifle. Then there's the flip side of the codebreaker, the unbreakable shield. Just as entanglement can be used to build a computer that breaks codes, it can also be used to create codes that are physically impossible to break. This is called quantum key distribution, or QKD. Secure communication requires a key. It's a secret string of data used to scramble and unscramble a message. The whole problem of cryptography is how to get that key to the person you want to talk to without anyone intercepting it. With QKD, you can use entangled particles to generate the key. You create pairs of entangled photons and send one from each pair to the receiver. Both parties measure the photons they receive. Based on the measurements, they can agree on a shared random key. Here's the clever part. If an eavesdropper, let's call her Eve, tries to intercept the photons on their way to the receiver, she has to measure them to read them. But the act of measuring a quantum particle fundamentally changes it. It collapses that fuzzy superposition. Her measurement will disturb the delicate entanglement between the pairs. The sender and receiver can then test a small part of their key. If they see that the correlations are no longer perfect, they know someone was listening in. They can throw the key away and start over. The laws of physics themselves guarantee the security. The act of spying is inherently detectable. This creates a perfectly secure communication channel. For military command and control, for diplomatic cables, for financial networks, this is a game changer. It's a defensive weapon. It ensures that your secrets stay secret. In an age of cyber warfare, an unbreakable shield is just as powerful as a sharp sword. So where does this leave us? We have the codebreaker, the all-seeing eye, and the unbreakable shield. None of them are death rays. None of them involve faster-than-light action. But they represent a fundamental shift in military and intelligence power. The quantum arms race isn't about who can build the biggest bomb. It's about who can control the flow of information. Who sees and who remains unseen, who knows and who remains in the dark. It's worth circling back to the science fiction ideas, just to be clear about why they fail. The quantum voodoo doll, where you manipulate one particle to affect a person somewhere else. This fails because you can't manipulate the particle's state. You can only measure it, and the outcome is random. You can't force it to be spin up to cause pain. You just discover it is spin up. The faster-than-light drone fleet, you want to control a drone on Mars in real time. The light speed delay is a huge problem. Can't you just have the controller entangled with a qubit on the drone so your commands are instant? No. Again, you can't send information, you can't tell the drone to turn left by forcing your local particle into a specific state. All you and the drone would have are two matching but useless strings of random data. The drone would still need a classical signal traveling at light speed to tell it what that data means. What we are witnessing is something more subtle and more real. We are learning to use the deepest, strangest rules of the universe to build tools. And like any tool, from a sharpened rock to a nuclear reactor, they can be used for good or for ill. They can be used to create new medicines, build better computers, and explore the universe. And they can be used to spy, to steal, and to gain an advantage in conflict. The weaponization of quantum entanglement isn't a single event. It's a process. It's happening right now in quiet, shielded laboratories in China, the United States, Russia, and Europe. It's a slow, difficult, and incredibly expensive race. They're not building weapons that go bang. They're building machines that think in new ways. They're building sensors that see the invisible. They're building networks that can't be tapped. The danger isn't a sudden quantum war with spaceships firing entanglement beams. The danger is a gradual shift in the global balance of power, a shift based on a quantum gap where one nation achieves a breakthrough and can suddenly neutralize the intelligence, economic, and military systems of its rivals without firing a single shot. The infrastructure of our modern world, built on digital ones and zeros and protected by classical encryption, is fragile. Quantum technology powered by entanglement is a tool perfectly designed to break it. So, can we weaponize quantum entanglement? Yes, absolutely. We just have the wrong idea of what a weapon is. We were looking for a hammer, and instead we found a key. A key that can unlock any digital door, and a way to build new doors that can never be picked. The battle for those keys is the real quantum war, and it has already begun.